So about this quantifier, so I want to talk about two logical equivalences, two types. So the first one I've already told you. So for instance, you have for all x, for all y, something. So something. Let's say this is a proposition about x, y. Then this one is logically equivalent to for all y, for all x, pxy. So the ordering of this for all can be exchanged. And another one is if you are talking about there exists x, there exists y, pxy, then this is logically equivalent to there exists y, there exists x, pxy. Is that okay? So logically equivalence means that whenever this is true, then this is true. Whenever this is false, this is false. Although I don't know what is the true value of this one, I don't know the true value of this one, I always know that the true value of both sides will always agree. Is that okay? True, then true. False, then false. Is that okay? Okay. Now, so this is ordering of the same type of quantifiers. And there is another one, the De Morgan. Okay. De Morgan's. So what is De Morgan's law? So De Morgan's law, I hope you still remember. If you are talking about logic, then then if you negate something like P and Q, then you will get what? So you make everything upside down. Okay, so it is negation of P or negation of Q, right? And similarly, if you negate P or Q, then this you will get, so this is equivalent, okay, equivalent to negation of P and negation of Q. Okay, so this is the De Morgan's law for propositions. But we can also talk about De Morgan's law of quantifiers. So for all x, let's do this, for all x px. So this says that this will be true only if and only if, okay, for all the x you test, p of x will give you true, right? Okay. So what is the opposite of this? The opposite. So here, this is true. This is true if all x that we test, maybe x0, x1, x2, that we test, we will have all of them are true. Are all true. But you want to say that, okay, so what is the opposite? The opposite is what is the case that it is false? So when is it false? When is it false? This is true when everything here is true, right? So when is it false? So it is false when, this is false when what? When sum of these x0, this x0, x1, okay, we will have px, sum of these x0, x1, I don't know which one, let's call it pxi, is not true. Is that okay? Is that okay? So this is false when this one. So if I write down the meaning of this one, sum of these x0, x1, x2, such that pxi is not true, I'm actually saying something like there exists a certain x such that px is not true. So that is the same as not px is true. Is that okay? Is that okay? So here, what does it mean? When this is true, this is false. When this is false, they're actually opposite. When this is false, then this is true. Is that okay? So they are opposite to each other. This one is always having an opposite value of this one. So they are opposite. So what does it mean? So it means that if I negate this one, their truth value will always agree. Is that okay? Okay. So it is like if you want to say that this one is not true, it is not the case that for every x px, then you are actually saying that. Why? Why you can say that? It is because there must exist some x such that not px is true. Is that okay? Okay, so this has also an interesting thing about inversion. So like this one, so whenever we have a not applied to this one, so this one is negated, this one goes upside down, this one is negated, right? Now here, similarly, when a not is applied on some quantifier, so a propositional function with quantifiers, then for all becomes there exists. And the original proposition becomes the negated form. Is that okay? Good. Then you know that negation of a negation is just cancelling the effect. So if I negate this one, then it is like negation of this. So we have another version of the De Morgan's law. So when you negate there exists xpx, it will be equivalent to for all x not px. Is that okay? Okay. So it's like when you tell somebody that it is not the case, it is not correct to say you can find some x such that px is true. Then you are actually implying that for every x that you can think of, the px value are always false. Right? So there exists a person who is very kind, okay? You say that this is not the case, okay? In the whole world, you cannot find a person who is very kind. So what does it mean? So you are saying that for every person that you can imagine, they are not kind. Okay, so this is like this. The negation of this one will be for everyone, then you have the opposite meaning rather than the original meaning. And this is also called De Morgan's law. So this is the De Morgan's law involving quantifiers. Okay, so we have that one. So let's do an exercise. Let's do an exercise about the best friend one. So let's say bxy is, so this is the best friend scenario. Y is a best friend of x. Is that okay? Y is the best friend of x, and then we have do something like everyone has exactly one best friend. So this is like for every x that you can imagine, there exists y who is going to be your best friend, such that for every other person z, such as z is not equal to y, then we will have what? We will have x, y are best friend, and what? And whenever z is not equal to y, this will imply that z is not a best friend of x. Is that okay? Okay. And then let's say we want to negate this. How do we negate? How do we negate? I don't know how to negate this one. I don't know how to negate imply. So first of all, let's change imply to something that we know. So P implies Q is equivalent to what? Anyone still recall? This is very, very, very important. So imply is something that is difficult to understand. Okay. P implies Q will be the same as, when is it true? When is it true? You think of the true case here and then write down the true case here. That will be, this will be true whenever P is false and whenever Q is true. Eh? Right? Right? So this one is not P or Q. Is that okay? Is that okay? Not P or Q. Not P or Q. Okay. So this one is P implies Q. Let us change it to not P or Q first. Okay. Not P. So this is Z is equal to Y. Or Q. Is that okay? Okay. Now let's do negation. Okay. So how do we negate this thing? So negation of the whole thing simply says that we are claiming it is not the case that everyone has one best friend, has exactly one best friend. Maybe some person has no best friend, or maybe some person has more than one best friend, right? So the negation of this one will be equal to, let's do the direct De Morgan's law. This is super great. Okay, you will be feeling very happy because it's so easy. Yeah, for all x, we change it to, very good, there exists x. And there exists y, you change it to, very good. And then for all x, for all z, okay, there exists z. Okay, now this is a whole thing, right? Right? This whole thing is this part and this part. You want to negate this. So you will have negation of this one. Negation of this one is negation of bxy. O. And then you negate this one. Okay? You negate this one. So how do you negate this one? This is something or something, right? So you negate this. So you change it to the negation. And that's it, done. Wow, super great. So you don't know what you are doing. Yeah, we don't know. Yeah, actually, I don't know, but this is correct. Okay. Who says it is correct? It is De Morgan. Okay. Because once we have proven De Morgan's law, so we are applying De Morgan's law again and again. As long as De Morgan's law is correct, we are applying things correctly. So let's see if we can take out some meaning of this one. So what does it say? So if not everyone has exactly one best friend, then you can find some particular person. This is the exceptional case. There exists some x. So this x is the person that we should focus on who does not have exactly one best friend. So in that case, then what? Then for every y that we consider there exists as such that either not bxy. Either not bxy, this means that this x may not have any best friend, has zero best friend, right? So this can be the case. Or what is meant? Or if this x has a certain, so if it is not the case, if this x has a certain best friend, let's call it y, then there exists some set such that z is different from y and bxz. So here it means that this person may have two best friends or more. Is that okay? Okay, good. Yeah, De Morgan's law. Yeah, it's great. Okay. Okay. So De Morgan's law is super useful. Okay, especially in circuit design or logic. So you can easily convert something from positive into negative or negative into positive. Okay, so this is the end of the lecture 2. Okay, so we have some time. Yeah, let's talk about a new thing, lecture 3. Lecture 3 is getting closer to proofs. Okay, so in proofs are actually made up of mathematical arguments. So what is the mathematical arguments? So So we write down, usually in the proof that we look at every day, you will see that someone write down some sentence, and some sentence, and some sentence. And then after a certain number of sentences are written, then there may be some short conclusion. So I will give you an example. So for instance, someone may write down something like, if it rains, I drive to school. So I'll drive to school. And then it says that another thing that we know is today it actually rains. It rains. And because of these two things, then we can have a conclusion. Therefore, so sometimes we use this one. This means therefore, or so, or thus. Okay, therefore, I drive to school. Okay, it seems makes sense, right? If it rains, then I will drive to school, and it actually rains. Assuming that this is true, assuming that this is, I'm writing down something that I'm not telling lie. So assuming that this is something that I really would do. If it rains, whenever it rains, then I will go to school. I will drive to school, and then let's say this is also something that is true too. Let's say today it rains. Then we can have a logical deduction. Okay, so we can conclude that I really drive to school today. Okay, okay. So this is called the mathematical arguments. So mathematical arguments usually have two parts. This part is, we call it the conclusion. So we can have something that is not known at the beginning, but it is due to the facts that we know. We collect the facts that we know. We try to think about what would that give us some new information. Okay, and then the facts that we have here, they are called premises. Premises. Okay. Okay. Now, so this works, right? Okay, but not all kinds of mathematical arguments are meaningful. So for instance, if someone says, if it rains, I drive to school, and then it rains, then my conclusion, let's say it is like, I'm going to have Pizza Hut tonight. And suddenly you're shocked, right? So it doesn't make sense. So this talks about rains and school, and then I'm saying I'm having Pizza Hut tonight. Yeah, it can't be related. Now, so for that kind of so that you can still call it mathematical arguments, but those are invalid mathematical arguments. Here, this is a valid mathematical argument. So there is a concept. Okay, so we are interested in the valid mathematical arguments. Valid mathematical arguments is the case that whenever the premises are all true, then the conclusion must also be true. Is that okay? So these are the arguments that we are interested. Okay? Okay? Now, okay, so let's say this is the premises like this. Okay, I can talk about another similar premises like what? If I'm tired, I want to sleep. Okay, so this is one premise, and let's say I'm really tired now. So what can we conclude? I want to sleep, right? Okay. So you see the two premises. So this mathematical argument says about rain and school. Another argument that I just mentioned talks about, oh, I'm tired and I want to sleep. Although they are talking about different things, but they are of the same form. Okay, the form is like this. So we have a proposition P implies Q as my first premise, and then I have P as my second premise. Then whenever I know that this is true and this is true, then I can conclude Q is true. Okay? Okay? So they are of the same form. So today we are going to look at, okay, what kind of valid argument form that we know or we use commonly every day. And this is one of the form, right? This is the form that if I know P, then Q will happen. And this time P actually happens. So we can conclude that Q will happen. Is that okay? Okay? So today we are going to look at a lot of different forms. And this is one of the many valid, so this is about valid argument form. Okay? So this is one of the valid argument form. And for a form to be valid, it has to be if the premises are all true. So if P implies Q is true, and so why is it valid? Why is it valid? It is because if P implies Q is true and P is true, then Q is true as well. Okay? If this is the case, if all the premises are true, the conclusion is true, then this is a valid argument. And we are using P, Q, P to represent general propositions, so this is a form, a valid argument form. Okay? Okay? So let me introduce to you. So all of them, you can check it whether they are valid argument form by using this logic, using this reasoning. Okay?